So, let us say, I mean, nowadays all amplifiers are fully differential. In other words, what it means is that so if this is VIP and this is VIM, this is VOP and VOM, then VOP minus VOM is simply A times VIP minus VOM. Okay. And those of you who have taken circuit classes will see why, I mean, fully probably already know why fully differential circuits are useful. And the reason is that if there is a disturbance on both VIP and VIM, right, which is very likely to happen in a practical situation, then the amplifier is only sensitive, at least in principle, to the difference between VIP and VIM. So, anything that is common to both VIP and VIM is not amplified, right. So, in this scenario, well, we still have, I mean, the amplifier will still have offset, and that causes all the the amplifier will still have input referred offset and flicker noise, and that still causes problems, right. So, however, fully differential operation makes it very easy for us to implement chopping with a slight difference in the chopping waveform, and that is the following, right. You can, if you have you can implement this block by right. So, if I call this A, B, C and D, this is A, B, C and D, and this is the chop waveform, and when chop is high, and these are chop bar. Okay. So, chop is a 50%, so this is the chop signal, this is TC, which is 1 over FC, this has 50% duty cycle, and this is chop bar, a chop complement, at least in principle that is also a 50% duty cycle square wave, and so when chop is high, A is connected to B and C is connected to D. When chop is low or equivalently chop bar is high, A is connected to D and C is connected to B. All right. Okay. So, as you can see, this is equivalent to if you want to draw a signal flow graph with this, you have an amplifier and the amplifier is amplifying the difference between the input and output, of course, and this the input here refers to VIP minus VIM and the output is VOP minus VOM, and there is of course the amplifier flicker noise Vn, right. And what are we multiplying the input with? You are multiplying it with the chop waveform, which is a square wave. Let me call that let me call this P of t. And this is y. And how does P of t look? Well, it is a square wave with 50% duty cycle and it goes between 1 and minus 1. This is 0 and this is Tc by 4, Tc by 4, Tc by 2 minus Tc by 2. This is 1 and this is minus 1. Okay. And so, this is P of t. And if the amplifier has got infinite bandwidth and if Vn is 0, what do you expect to see? Well, x of t, I mean ideally amplifier bandwidth is infinity, right, and y of t, I mean, or let us call this V sorry VO1 of t, which is the output voltage just before the low pass filter, is simply x of t multiplied by P of t multiplied by A by P of t again, which is nothing but x of t times A times P square of t, which is P square of t, as you can see, is 1. So, this is A times x of t. So, when compared to using a cosine modulating signal, we can see that we have a gain which is A rather than A by 2, all right. And what comment can we make about Vn? If let us say Vn is a DC offset, then at the output of the amplifier it is amplified offset, then it is getting multiplied by a 1 minus 1 tone. It on average will be 0 because the low pass filter is going to remove this, right. So, I mean, so basically under ideal circumstances it works. Now, the question is what happens, of course, we know that in the real world no amplifier is going to have infinite bandwidth. So, the question is okay, let us see what happens when you have an amplifier with a bandwidth which has got a bandwidth of 1 over 2 pi tau, right. Okay. So, the transfer function of the amplifier is we assume it is a single pole model with a bandwidth and that bandwidth corresponds to time constant of tau. Now, the question is what happens to y of t, right. In other words, we would like to understand what all inputs can lead to an output at DC. So, again we go back to our, so this is the original signal flow graph. Now, it is time to draw the adjoint. So, this is x hat of t, this is p of t, this is v n hat, this is a by 1 plus s tau, this is p of t again, this is the low pass filter, this is y hat of t. So, again what do we need to do? We apply DC here. What do you get here? 1 volt. Now, that gets multiplied, let us call this at point A. What signal will you get? You will get P of t, P of t as, and by the way this should have been P of minus t, but since P of t is an even function, it is the same thing. So, what do we do now? What you get at A is basically a signal like this. So, this is 1, this is minus 1, all right. Now, what comment can you make about the signal at B? A square wave is passed through an amplifier with a DC gain of A and a bandwidth and a time constant corresponding to tau. So, what do you think you will expect to see at the output? Let us assume that, I mean, remember what is this duration? This duration is
TC.
The chopping period Tc. Right. So, what comment can you make about, let me draw that in blue over the same picture here. What comment can you make? How will it look like?
The average gain.
No, you take a square wave, pass it through a single stage amplifier with a DC gain of A.
Exponentially.
Yeah, it will basically, it will do this, and if tau is much smaller than Tc by 2 or Tc equivalently, we will do this, then do this, and so on, right. So, the assumption is tau is much smaller than
TC.
Tc by 2. Okay. Now, what comment can we make about x hat of t? The signal at x hat of t.
It is multiplied.
The blue signal here is going to be multiplied by
P of t.
the red signal here, right. So, what comment can we make? So, what will happen to when?
Only positive will come.
Yeah. So, basically you will see something which you will see something like that, right. This red part is the same as this blue part, right. Then in the second half cycle what happens?
It is like again positive.
Yeah, you multiply it by -1. So,
This one with the negative of the.
yeah. So, basically what you will see is something like this, then again you will see something like this, and so on. Okay. So, what is the peak amplitude here? It is going to be A, this is minus A, all right. And what do you think you can? So, first thing that you observe is that the what comment can we make about H 0? I mean, what do you think is the area of this part? It is the same that hatched area is basically something, is an exponential that goes from with a height of
What, like A2?
2a and a time constant of tau, right. So, the area of this this hatched part, which is the same as the area of that hatched part there, is nothing but 2a times tau, right, which is nothing but 2a e to the minus t by tau dt integral 0 to infinity, which is nothing but 2a times tau. So, what comment can you make about so basically the average value of this is the same as the average value over half a cycle of Tc, which is basically A times Tc by 2 minus 2a tau divided by Tc by 2, which is nothing but A times 1 minus
Tau by T. Tau by TC.
no, think carefully,
Okay, 4
4 tau by Tc. Okay. So, what is the average value of x hat of t is A times 1 minus 4 tau by Tc. So, what is the conclusion? What does this mean?
Time constant is 0.
Yeah, of course, if time constant is 0, you will get A, which you expected. But so what is the conclusion? We analyzed the adjoint network, we applied DC at the output port and found that the DC value of the input port is A times 1 minus 4 tau by Tc. So, what does this mean as far as the original signal flow graph is concerned? In the original signal flow graph, H 0 of j 2 pi 0 is A times 1 minus 4 tau by Tc, right. So, what conclusion? So, finite amplifier bandwidth reduces
Gain.
DC gain of the chopped amplifier. All right. Okay. The next thing, what is the period of the waveform at x hat of t?
The period is TC by.
Yeah. So, the period of this waveform is Tc by 2. So, when you expand this in a Fourier series, what all components will you get? What all frequencies will you see?
Like 2f.
You will see. So, Fourier expansion is has components at 2 Fc, 4 Fc, 8 Fc, 6 Fc, etc., etc. All right. And so what comment can you make about so what? How does this?
Input at frequency at 4fc, 6fc, multiple of 2fc will fall back
Yeah.
to the DC.
So, very good. So, what does this mean? This means that inputs frequency components at multiples of of 2 Fc will appear at as DC at the output. Okay. So, this basically means that there is down conversion of input signal components at all even multiples of the chopping frequency. Now, the question is what happens to the, what is the gain from an input, for instance at 2 Fc to
All those.
to the output at DC. You understand?
Yeah.
So, we would like to, I mean, we know that input components at multiples of 2 Fc will fold or will get translated to DC. Now, there is a, I mean, a question to ask is, what is the gain from an input at 2 Fc to output at DC. So, how do we, I mean, how do you think we can find that out?
By doing Fourier expansion.
Yes, Fourier expansion of this periodic waveform, right. Now, we do not do the Fourier expansion of the Fourier waveform, but let us get an idea if by, I mean, we can get a good approximation by basically recognizing that this output is simply 2a, I mean just a minus,
E power of
so x hat of t is simply a, right, plus a waveform which kind of does okay, and so on.
the peak is 2a.
Yeah, this is 0 and this peak is, this is 2a. Right, and the time constant is tau. All right. So, this can be approximated as, you can think of this as an impulse with an area of 2a tau. Right. So, this is a periodic impulse train with an area of 2a tau. All right, and this is nothing but dc by 2, right. And if you have a periodic impulse train, you know that all the Fourier impulse train in frequency domain is also an impulse train in the time domain, and all the Fourier coefficients have the same value. So, what is the, so if you know the DC component of the impulse train, the strength of all the harmonics is also the same thing. So, what is the DC component of this value? It is nothing but 2a tau divided by Tc by 2, which is 4a into tau by Tc, right. So, all the Fourier coefficients are have the same magnitude, and I mean, you know, and that is because we have approximated this narrow exponential pulse by an impulse function, right. So, that at least for the first several harmonics, harmonic transfer functions, you basically this value will be accurate. So, what and because this is negative, so this must be all must be negative, and this must be all the coefficients must be minus 4a tau by Tc. So, what comment can you make therefore of h minus 2 of j 2 pi times 2 fc
like minus 4a.
is nothing but minus 4a times tau over Tc, right, and which is also approximately equal to h. So, h minus 4 of j 2 pi times 4 fc, etc. Right. And what is the sanity check?
DC we can check.
Of course, sanity check is DC, of course, we already know, right. But what comment can we make about I mean h minus 2 of j 2 pi 2 fc? Is there a sanity check for that we can do for that?
We can give the tau net to 2fc.
As tau becomes 0, what do you expect?
It has to be 0, sir.
Yeah. So, as tau becomes 0, right, remember that as tau becomes 0, the output is simply a times x of t, right, because p square of t is 1, right, and nothing, and you can see that from this diagram too. As tau becomes 0, this will simply this waveform will simply become a constant a. There will be none of that exponential tail, right. So, as tau tends to 0, the h sub minus 2m of j 2 pi m 2 pi into 2m fc becomes 0, tends to 0. All right. Okay. The next thing is what comment can we make about the harmonic transfer functions to from the noise source to the output, right, and for that what do we need to do?
At B only we have to.
Yeah, we have to look at the waveform at B. The waveform at B is shown in blue, that is this waveform here, right, and that is basically a square wave. So, what comment can we make about as far as Vn hat Vn to y of t is concerned in the original signal flow graph? What comment can we make about h 0 of j 2 pi 0?
Average it is 0.
That will simply be the DC value of this periodic waveform, right, and that is 0, and that we knew already, right. If you apply DC there, it is going to get chopped to plus and minus p of t, and that is going to be completely eliminated by the low pass filter. Okay. And of course, there are higher order harmonics, and so I mean, and what is the fundamental frequency of this waveform at B?
That is the FC.
That is simply that has a period of FC, a period of TC, which basically means the Fourier series has got components at multiples of FC. However, as you can see, this is since the duty cycle of the square wave is 50%, it will only have odd harmonics, right. So, H plus minus 1 plus minus 3 plus minus 5 etc. are non-zero, right. And what does this mean? Noise from multiples of
FC.
From odd multiples of
FC.
FC will appear at
DC. And the
appear at out. This is an example of the use of adjoint techniques, right, where you can also try and do the, I mean, you could the adjoint makes you see very clearly what is going on, right. In principle, you could, I mean, finally, when you have a circuit, you can always analyze it, right. So, you could in principle go on putting in an input tone at FC and then put it at 2 FC and then arrive at the same result. But this is, that's kind of, yeah, it's messy, and you do it once for the offset and once for Vn and once for x of t, and that too for each frequency. This applying the adjoint technique basically saves a significant amount of labor. So, this is a very useful trick to